So what have we covered in this block? We've talked about proofs by induction in by analogy with definitions by recursion. And in particular, we've looked at the example of lists. And we've seen that you can prove properties for all finite lists, and in some cases for all lists, irrespective of whether they're finite, partial, or infinite. And so I think I've given you an introduction. I've shown you a couple of examples there. There's some exercises on which you can build. But also the same techniques can be used over data types and other Haskell data. So if you remember, we did an interpreter and an expression case study a few weeks back. It's possible to prove that the interpreter or compiling and executing gives the same results for all expressions in that language. And just one final thing to say about proof for functional programs. It's different from the way you reason about imperative programs with invariants and so on. It's direct reasoning. We read the definitions of functions as logical properties and we deduce things from them. It's a very direct way. Reading the definitions as logic allows us directly to deduce. And that's what we've been doing with the examples we've seen in this block of using the definition of map and plus. That's allowed us to prove properties. For example, if you join two lists together, it doesn't matter whether you map a function over them before or after you join them, for instance. And it's nice to be able to use, as a matter of routine, to use logic like this to prove crucial properties of library functions like plus and map. Okay, well that's it for this set of videos. I just want to wish you happy functional programming. I hope you found functional programming in Haskell an enjoyable thing to learn, and that you get a chance to use it in practice, in anger, as it were, either in Haskell or indeed another language sometime soon. Thanks very much.